Hello, my name is Byul-gang. Today I will begin my presentation on understanding air traffic controller task load variability under adverse weather and high traffic scenarios. Let's start from introduction. What is the air traffic controller's task load? Task load represents how much time is needed to deal with events that require decisions and action by air traffic controllers. As you can see images below, it shows simple comparison of low and high air traffic controller task load. For example, as shown here from a previous study, the task load formula is expressed as the sum of the weight for each event I multiplied by the expected number of type I event per hour. Here we can see the relationship between air traffic controller task load and traffic volume. As the graph shows, task load increases as traffic volume increases, which is quite obvious. But the task load is not determined by traffic volume alone, but also by other factors such as weather, airspace structure, or operational complexity. So at this point, let's talk about why is task load analyzing and managing is important. Air traffic controllers have a limit, known as the maximum task load they can manage. When the task load exceeds a manageable threshold, it diminishes air traffic controllers' concentration and performance, which highly related to significant safety risk. Thus, analyzing and managing air traffic controllers' task load is critical for ensuring the safety of air traffic operations. The goal of the study that we analyze how air traffic controller task load varies under different air traffic operational scenarios. The scenarios include high traffic, where congestion arises from increased traffic volume, and normal traffic, where the traffic level remains average, and adverse weather, where weather factors cause additional airspace congestion. Now let's move on to the methodology. We classify air traffic controller tasks into three primary tasks for calculating air traffic controller task load. First, transition task. Second, recurring task. Lastly, conflict prevention task. Now, let me explain each task in a bit more detail. Transition tasks, which are performed whenever an aircraft passes through the airspace. These tasks include initial contact. It means first radio communication between an aircraft and air traffic controllers, meters to feet unit conversion, and initial planning. It means review of routes and altitude when an aircraft enters the sector, and coordination with adjacent air traffic controllers and handoff. It means transfer of control authority to the next air traffic controllers and confirmation of flight plan. Next, recurring tasks, which involve routine traffic structuring. These tasks include altitude and heading change instructions. And conflict prevention tasks, which encompass the detection and resolution of potential conflicts. This includes conflict avoidance at route intersections and prevention of overtakes due to speed differentials along the same route. And the task load of each task is quantified by multiplying the frequency of task occurrences by the average time spent per task. In this study, a frequency of task occurrences was extracted from real-world flight trajectory data, and the average time spent per task was measured through field studies, or derived from analysis of standard ATC phraseology. Next, I will be presenting the numerical result of our study. We Analyzed task load variability in an actual sector under high traffic, normal traffic, and adverse weather scenarios. In this study, the West Sea North sector, which has the highest traffic volume in South Korea, was selected as the study area. The frequency of each task was extracted from ADS-B trajectory data July 2019. In addition, weather information was obtained from SIGMET, also July 2019. Let me explain the data set and scenario definitions in more detail. The adverse weather scenario was defined based on the periods when SIGMET was issued. During July 2019, a total of 10 SIGMETs were issued in the West Sea North sector. Trajectory data corresponding to these all SIGMET periods were extracted to calculate the frequency of task occurrences, which was then used to estimate the adverse weather task load. And during these periods, the occupancy demand was calculated to reach up to 9 aircraft. Occupancy demand means how many aircraft on air traffic controllers is managing at the same time. Meanwhile, the normal traffic and high traffic scenarios were defined for the remaining periods in July, excluding the hours when SIGMETs were issued. Within this data set, the occupancy demand ranges from 0 to 15 aircraft. The top 30% of occupancy demand was classified as the high traffic scenario, while the remainder was defined as the normal traffic scenario. Trajectory data within each scenario were used to calculate the frequency of task occurrences for each scenario. This is analysis result of normal traffic scenario. Under the normal traffic scenario, transition task, you can see that blue line, place the heaviest burden on air traffic controllers, followed by recording task, and lastly, conflict prevention task. This is task load variability analysis result of a high traffic scenario. As you can see that figure, under the high traffic scenario, recording task placed the heaviest burden on air traffic controllers, followed by transition task, and lastly, conflict-related task. This is analysis result of adverse weather scenario. Under the adverse weather scenario, recording task placed the heaviest burden on air traffic controllers, followed by transition task, and lastly, conflict prevention task. This is analysis result of the comparison of task load between the normal and adverse weather scenarios. Each task has different scale, so we couldn't direct comparison to each other, so we normalize based on reference value. To be more specific, in this analysis, the task load corresponding to the average number of aircraft in the normal traffic scenario is used as the reference value, and the task load of both the normal and adverse weather scenarios were normalized to this reference value for comparison. The x-axis represents the number of aircraft, while the y-axis represents values normalized by the reference. The solid line denotes the normal traffic scenario, and the dashed line denotes the adverse weather scenario. The results indicate that complex operational conditions such as adverse weather significantly increased the task load. Specifically, the frequency of traffic structuring tasks increased due to adverse weather avoidance, and the total utterance time increased as additional ATC terminology was required, resulting in a task load more than 2.26 times higher than under normal traffic conditions. Meanwhile, transition task increased only about 1.04 times compared to normal traffic conditions, because the transition time differed by merely 36 seconds. In contrast, conflict prevention tasks were reduced to approximately 0.8 times the level observed under normal traffic conditions. This reduction occurred because under adverse weather conditions, air traffic controllers often issue direct instructions to expedite aircraft exit from the sector. So consequently leading to fewer aircraft and lower frequency of conflict prevention tasks. Furthermore, since the analysis was based on trajectory data that had already undergone traffic structuring, the reduced task load of conflict prevention tasks can be interpreted as shifting toward transition and recurring tasks, thereby increasing their task load. Conclusion. In this study, we have analyzed how air traffic controller task load varies under different air traffic operational scenarios. Under the normal traffic scenario, transition task place the heaviest burden on air traffic controllers, while under the high traffic and adverse weather scenario, recurring task place the heaviest burden on air traffic controllers. And in the normal traffic and adverse weather task load comparison part, we can find visible increase in recurring task and minimal change in transition task load, while we also find a decrease in conflict prevention task load. Lastly, this study provides a comprehensive understanding of air traffic task load variability and offer an important indicator for the effective management of air traffic controller task load. The following is the future work. Since the analysis relies on real-world flight trajectory data already structured for traffic, the frequency of conflict prevention tasks tended to be underestimated. Therefore, future research should generate flight trajectory data under various conditions through simulation and recalculate the frequency of collision tasks, so that a more comprehensive comparison of task load can be conducted. In addition, the research flow that I personally want to do is by analyzing the relationship between task load indicators and traffic activity. I aim to convert task load into the number of controllers required in a sector. This is the end of my presentation. Thank you for your attention.